Now that I have covered the formal definition of limit of a function fx as x approaches some value a, let us see some examples of limits of a function. Let me take my favorite example of a stone dropped from a height. The function I will consider is average speed of the stone during the interval starting at time t seconds from the time it dropped and ending at t plus delta t seconds. So the duration of the interval is delta t seconds. Notice this time the average velocity that we are going to work out shortly will depend on delta t, that is the time interval, and also on the start time of the interval t. So we can expect the average velocity to be a function of two variables, namely t and delta t. Distance traveled till the beginning of interval, that is till t seconds, st is equal to 5t square. Distance traveled till the end of the interval, that is till t plus delta t seconds, 5t plus delta t whole square, 5t square plus 10t into delta t plus 5 delta t square. Delta s, the difference between the two distances, is equal to 10t into delta t plus 5 delta t square. Average speed is equal to delta s divided by the time interval, which is delta t. Notice this becomes 0 by 0 if delta t, the time interval, is taken to be 0. So for a non-zero delta t, average speed is equal to 10t plus 5 delta t. Notice this is a function of two variables, t, which is the start time of the interval, and delta t, which is the duration of the interval. Now I am going to find the limit of this function as delta t approaches 0. This will eliminate delta t from this function. The remaining will still be a function of t. As delta t becomes smaller but not 0, this term becomes smaller with no lower limit. So the limit is 0. So limit of average velocity for period t plus delta t as delta t tends to 0 is equal to 10t. This portion becomes 0. So the instantaneous velocity at time t is 10 into t. The only difference between this and the calculation done in earlier video is, earlier we had taken the start of the interval as 3 seconds. This time we have kept the start of the interval as a variable t. So now we can put any value for t in this expression and find the instantaneous velocity at any time. Try for t is equal to 3. T is equal to 3 seconds. The result will be same as in earlier calculation, which was done specifically for 3 seconds. For my next example of limits, consider a bucket with say 10 liters of water in it. I dip a giant mug into it and take out half of the water contained in the bucket. The bucket is left with half of 10 liters. I repeat the exercise. The bucket is now left with 1/4 of 10 liters. I repeat it again. 1/8 of 10 liters is left. Let me tabulate it. number of mug dips, 1, 2, 3. After the nth dip, the amount of water left will be 1 by 2 to the power n of 10 liters. After each dip, the quantity of remaining water reduces. How much water will be left after 100 dips? 1 by 2 to the power 100 of 10 liters. Incidentally, this is approximately 10 to the power minus 29 liters, which is lesser than 1 molecule of water. Physics tells us it is not possible to split and make half of a molecule, but for mathematics, there is no limit in discussing, reasoning, and calculating about quantities with no limit to how small they become. Will it be 0 after 100 dips? No. Will there be 0 water left after 1000 dips? Still no. I can get the remaining water quantity to be as little as I want, with no limit to how little a quantity is left, by increasing the number of dips as much as needed, with no limit to how many times I need to take the dips, how large a number of dips I need to make. This number of dips, a very big number with no limit to how large it can be, a number larger than any known number, is denoted as infinity in mathematics. Notice, this is not an actual number, and it does not follow the normal rules of addition, subtraction, multiplication, or division, etc. So, what we have shown here is limit of remaining water as the number of dips approaches infinity is equal to 0. Or in other words, limit of 1 by 2n as n approaches infinity is equal to 0. For my next example, I choose a function which is not expressed by a mathematical expression. Rather, it is described in words using logic of equality and comparison of two numbers. I define fx as 0 for all values of x except for x is equal to 5, and 1 for x is equal to 5. It is a peculiar function. Let us attempt to draw a graph of x versus fx. And here is 5. As long as x is below 5, the value of fx remains 0 till before x reaches 5, and for all values of x above 5, the value of fx remains 0. What happens when x is exactly equal to 5? Value of fx becomes 1, but it is for exactly equal to 5. That means this line, which represents value of x, goes all the way till exactly before 5 and a very small quantity before 5. This gap in this line here is an extremely small, actually zero sized gap, and the size of this dot is a zero sized dot. For all values of x, even those very close to 5, very close to 5, value of fx is 0. In physical reality, when you judge equality of any two quantities, there is always a range, often an approximate range of values which are considered to be equal. Suppose you have a bag containing 5 kg of sugar and another bag which contains 5 kg and a little more, maybe 5 kg plus 0.1 grams of sugar. These two bags will be considered equal for all practical purposes that you can measure. If you have access to extremely precise weighing machines, maybe you can find the difference and declare them as unequal. But if the difference was, instead of 0.1 grams, if the difference was, let's say, 10 to the power minus 6 grams, then even the most precise machines of the world developed so far will probably not sense the difference, and they will declare them as equal. But in mathematics, there is no such limitation. That is why probably the saying, your thoughts have no limits. I can declare a number as not equal to 5 even if it is lower or higher than 5 by a quantity orders of magnitude is smaller than 10 to the power minus 6, like 10 to the power minus 12 or any quantity howsoever small. And my peculiar function fx will continue to remain 0 for all such values of x which are not equal to 5. Yes, it will become 1 when x becomes 5, but only for x exactly equal to 5. For such a function, what is the limit of fx as x approaches 5? For all x such that x minus 5 is less than delta, that means x is within plus or minus delta of 5. No matter how small the delta is taken to be, no matter how close to 5 we reach, no matter how narrow this band becomes, but for which x minus 5 is not 0, it is greater than 0, which means x is not equal to 5, it is very close to 5. How close depending on delta, how small delta you choose, but it is not 5. For all such values, fx is 0. So the limit of this function as x approaches 5 is 0. Even though the value of the function at x is equal to 5 is 1. I hear you asking, where in real life do we get a peculiar function like this? What is the use of studying such hypothetical nonsense if we are never going to encounter such things in real life? Well, the real life functions never actually behave like the one described here, but in some cases they come pretty close to this. And this knowledge actually helps in those cases. You will not have to wait very long to find out actual physical examples where this knowledge is used in physical world. We will come across such problems within possibly this year of study, within class 11 or 12. Example is a function fx which is defined as 0 for all values of x less than 5, 1 for x equal to 5, and 2 for x greater than 5. Let us draw a graph of x versus fx. As long as x is less than 5, value of fx remains here 0. Exactly at x is equal to 5, value of fx becomes 1, but it's only a 0 width point. For any number of x, for any value of x greater than 5, the value of fx becomes 2. I think a full detailed discussion is not even required to show that limit of fx as x approaches 5 from the lower side is 0. Limit of fx as x approaches 5 from the lower side. This little minus sitting here is used to denote it is approaching x from the lower side. And limit of fx as x approaches 5 from the upper side is 2. Whereas fx for x is equal to 5 remains at 1.